I have a course by Artem Dudko. New estimate from below on the Hausdorff dimension of some integers.
Thank you very much for the introduction. I gave a talk about a year ago on estimates from below on the Hausdorff dimension of the Julia set of the Feigenbaum polynomial. This is a part of the same project, which is now completed, at least this part. But since a year ago, it was generalized to larger sets of maps and proofs simplified, and also we have a few more applications. Not just the Feigenbaum polynomial now, but also various other Julia sets. Just a brief reminder what we call a Julia set. By definition, given a polynomial f of z, its field Julia set is a set of non-escaping points, and the Julia set is a boundary of the field Julia set. And here just a few nice pictures of various Julia sets. And this is one of the important examples, Julia set of the Feigenbaum quadratic polynomial d square plus c, fake constant approximately -1.4, from which the normalization in complex dynamics originated. And now let me briefly describe the construction, the main construction of our paper with Igors and Warwick. But for the case of quadratic polynomial d square plus c with real c. So to obtain estimates on the Hausdorff dimension of the Julia set of this polynomial, we start with taking large capital R. For our purposes, actually R equal to 2 is sufficient. The only condition is that it should contain the Julia set inside. We cut the disk of radius R around 0 into 2 half disks in the upper half plane and the lower half plane. And construct 2 power k preimages of these half disks under k minus first iterate of our polynomial. And it's not hard to see that this will be a Markov partition. And here is an illustration. I think this is for z square minus 1 for the Basilica map, for the Basilica Julia set. So this is our 2 half disks of radius 2, as you can see. We take first preimages, we get 4 pieces. Next preimages, we get 8 pieces, etc. So here is, for instance, partition.
This is okay due to the fact that this is a real polynomial. So R is forward.
Yes, yes, yes.
Otherwise, you would not have.
That's right. Yes, we assume that C is real, that we have quadratic polynomial for real C. I will explain the general case later during my talk. And this is just illustration. Here is partition of level 12. Oh, actually, it was for the Feigenbaum polynomial, not for the z square minus 1. For z square minus 1, I will show picture later. So we have our partition. Using this partition, we introduce so-called Macmillan matrix NK. Its entries are maxima of the derivatives of preimages of pieces of Markov partition inside other pieces. Namely, if we have indices I and j such that preimage of pj intersects preimage of pi, well, that basically means that preimage of pj lies inside preimage of pi. Then mij is the maximum of the derivative of polynomial pc z over all these points z from this intersection. And then we take inverse power. So basically it shows how much our elements of Markov partition shrink under preimages. And if preimage of pj's piece does not intersect pi's piece, we set the corresponding element of the matrix equal to 0. So we have 2k by 2k matrix.
There is a typo there, right?
What?
If it's empty.
There might be typos.
No, in the last line.
It's okay. If it's not
non-empty.
non-empty, then we have some non-zero number, some transition.
Yes.
Oh, yes.
So here was comma, and this is the second part.
Comma, excuse me,
Otherwise, yes. Okay, and also we denote by mk of t the matrix with this elements raised to power t. We set delta k to be the infimum of the positive values of t, for which the spectral radius of the matrix equal to 1. Or we set delta k equal to infinity if such t does not exist. Or rather, if spectral radius of this matrix is always greater than 1. So I observed that for t equal to 0, this matrix has all non-zero values equal to 1, and so its spectral radius is automatically greater than 1. And the main result in this case, our estimate states that for this given polynomial PC, for this real C, we have that Hausdorff dimension of JC, of the Julia set, is greater than delta K for every integer K. This is a simple version of results in the particular case. And now let me explain a few applications. So first application, the one which I mentioned in the talk a year ago, then it was focused on this application. It's for the Feigenbaum parameter approximately minus 1.4, which is the limit of the cascade of period doubling parameters for real quadratic maps. Previously, jointly with Scott Sutherland, we showed that the Julia set of the Feigenbaum polynomial has Hausdorff dimensions strictly less than 2. So it was some open question which we were able to resolve using the computer assistance. And now application of the above mentioned result, we show jointly with Igors, Gorbovickis, and Warwick that the Hausdorff dimension of this Julia set is greater than 1.4978. So we were not able to reach 1.5. We don't know what are the reasons. Is it because the dimension is less than 1.5, or we don't have enough computer power or accuracy? But that's the best we could get so far, which is already quite strong because previously known best lower bound for quadratic Julia sets was 4/3. So it was known that there exist real quadratic Julia sets with Hausdorff dimension greater than 4/3. Our result substantially improves this lower bound on the supremum of this Julia sets. And just a remark, to obtain this result, we had to take Markov partition of level 28. So take 28 preimages of the initial two half disks. Next result is about parabolic periodic points. So recall that a periodic point of holomorphic map is called parabolic if the derivative of the return map for this periodic point is equal to exponent 2 pi I theta for some rational theta. So we denote by Cn the parameters closest to parabolic parameters closest to 0 such that Pcn has period 2 power n parabolic point. And it is known that the mapping d of c equal to the Hausdorff dimension of the Julia set C for real C is smooth when C is inside hyperbolic components of the Mandelbrot set, in particular between two consecutive parabolic periodic points.
In fact, even a real analytic.
Yep. But since we resolve here the question of smoothness, for me smoothness is enough. And moreover, Ludwik, Jaksztas, and Michel Zinsmeister calculated asymptotics of the derivative of this Hausdorff dimension for real C near Cn. The expression of this derivative depends on the value of d of Cn. During previous talk, Ludwik Jaksztas explained more recent results about similar behavior for certain parameter c equal to -2. So the results of Ludwik and Michel imply, as they mentioned in their papers, the following conditional theorem. If the Hausdorff dimension of the parabolic Julia set at Cn is greater than 4/3, then the Hausdorff dimension is Celan smooth near Cn. we rigorously confirmed that the Hausdorff dimension is indeed greater than 4 over 3 for all these parameters Cn. And so the Hausdorff dimension is indeed smooth on the whole segment from the Feigenbaum parameter minus 1.4 something to minus 3 over 4. So this is the second application. And so the third application is rigorous graphs of lower bounds for the Hausdorff dimension of Julia sets of GC for C on segment from -2 to 2. So this is I think a plot of 21,000 calculations, rigorous calculations for various small segments, showing for each corresponding point lower bound of the Hausdorff dimension of the Julia set. And here is zoom in near point -1.6 to illustrate how this looks like. So for each of the small segments, using precise computer bounds, we obtain uniform lower bound on the corresponding segment. That's why here we have piecewise constant graph of the lower bound.
Could you show the previous slide?
Yep.
So at point 25, there should be this continuity of Hausdorff dimension of
Which one?
0 or point 25 to the right of 0.
0.25 here?
No, 25. No, before.
Oh, here?
Here, because there is discontinuity, because we have here Julia set becomes disconnected. There is parabolic multiplication for 1 second, 1/2 point. There is jump up here, and then it should be rather decreasing. Maybe you don't study here the whole Julia set, but only part of this, which is obtained from the original boundary. But there is suddenly this Lavor's bifurcation, and much more becomes belongs to Julia. So there is definitely there is a hue. There is this continuity of dimension somewhere here. So, and then it is going down. So I suspect that this picture shows not the whole Julia set, but only this part, which is a remnant of the old one, of the circle, not. No, I'm guessing. I don't know. And if this graph of Hausdorff dimension Julia set is definitely incorrect.
Well, this is lower bound.
This is lower bound. So probably, yeah. So probably indeed you study only this part of what happens with the original boundary of basis of infinity. You don't consider new pieces of Julia set which are due to Lavor's method.
So
Okay,
another thing.
I understand. Okay.
Another thing that is that we can, by taking deeper and deeper Markov partitions, we can obtain more and more accurate bounds, but we don't know how fast they converge to the limiting to the Hausdorff dimension. We know that it is convergent for hyperbolic parameters, for parabolic parameters, but because the speed is different, it's natural that even each of the lower bound, we can get sequence of these graphs. It will be continuous, but in the limit it might become discontinuous. But in fact, so this is a rough picture. As you see, a finer picture here. The graph is locally constant, so it's had, in fact, lots of discontinuities. Anyway, these are just technical remarks. And as Ludwik Jaksztas mentioned during his previous talks, he used these estimates which we obtained to get some empiric estimate lower bound for the limit of the derivatives of d of c when c approaches -2 from positive direction. Okay, and one more application. It's about other renormalization fixed points. So just to briefly recall what is renormalization. So if we have a ramified covering of degree 2 from a disk to a larger disk, it is called renormalizable with period p if there is certain return map on a smaller domain, which will be again a ramified covering of degree 2. So like on this picture, we have our initial map with its Julia set, and there is this a small disk U prime around critical point, which under third iterate returns to a larger disk, so that the restriction of the third iterate under U prime is again quadratic-like map, ramified covering of degree 2. And the corresponding restriction is called pre-renormalization, and appropriately rescaled pre-renormalized map is called renormalization of F. So this is a brief recall. Assume that the domain U is the definition of F as above is symmetric with respect to real line and 0. And we can encode the period of the critical, the orbit of the critical point for such map F using permutation on n symbols. So S0, etc., Sn-1 are different numbers from 0 to n-1 in some order. And this encoding shows when j's iterate of 0 is less than k's iterate of 0. And it is known that a real infinitely renormalizable map F, by definition, a real infinitely renormalizable map F has stationary combinatorics if the corresponding permutation of all successive renormalization is the same. So the fourth application of our result, we also calculated lower bounds on the Hausdorff dimension of several periodic point of renormalization. So here in this table, you see several permutations of period up to 6. Corresponding parameters C, for which the map Z square plus C has this given combinatorics, and lower bound which we obtain on the Hausdorff dimension of the corresponding Julia set. Okay. Any question about the results in the applications? If not, let me move to the next part of my talk to more detailed results. The general case, not just for quadratic polynomials. So we obtain a result for partitioned holomorphic dynamical systems, which by definition is collection of maps on disjoint domains. We assume that each of the maps is a covering map of a J onto its image, possibly branched, so it may have critical points. Questions? So we assume that we have a Markov property that is for each pair of indices I and J, the image of UI either contains UJ or is disjoint from it. And we assume certain transitivity. That is for each map UJ, for each domain UJ, there exists a sequence of maps from our system, composition of which is defined on the subset of UJ, and maps it surjectively onto the union of all sets.
Isn't
So that is
Van Strien and other people called box mapping?
not quite. So there are differences in the definitions, but it resembles box mapping, and such conditions were studied previously for different purposes. Okay, so given such system of maps, denoted by C of F, it's critical set. C of F, it's post-critical set. And for integer k, for Z from the domain of system F, not avoiding post-critical set, and for positive T, we consider the geometric tree pressure at point Z equal to the sum of derivative of case iterates of our maps at the images of Z, and absolute value raised to power minus T. So this is natural usual geometric tree pressure, but defined for such a system of maps. It's defined as lim sub when k goes to infinity, 1 over k logarithm of theta k. So theta k are partial sums of the Poincare series for the system. And for important cases, this value p of ztf does not depend on z. In fact, even on larger set, it does not need to avoid post-critical set. It should avoid so-called exceptional set. So Felix showed that this would not depend on z for rational maps, for instance, but to avoid proving this in generality, we just introduce P of Tf as an infimum over all z of the pressures corresponding to point z. And define Poincare's exponent Tf as infimum of all t for which the T pressure is less or equal to 0.
I'm not sure whether it should be called Poincare exponent. Poincare is usually related with convergence of divergence of a series, not about exponential.
Mm-hmm.
So I don't know how to convert.
Mm-hmm.
And it's usually exponential is usually related if there are no critical points related with related with Hausdorff, we call it hyperbolic dimension, and this Poincare convergence of divergence of Poincare series is another box dimension.
I see.
In case Lebesgue measure is 0.
I see. Okay, thank you for the comment. Well, it might be that Poincare exponent is not the best name, but anyhow, this is a quantity which we denote by Tf. And using some area argument, it's not hard to show that P of 2 is always less or equal to 0. Because 2 corresponding to calculating pre-images of areas of given disk. So it's not hard to show that Tf is well defined. So as Felix mentioned, so Tf is related to the hyperbolic dimension of the Julia set, which is the supremum of the Hausdorff dimensions of all forward invariant hyperbolic subsets. And in particular, we have always that hyperbolic dimension is less or equal to the Hausdorff dimension. And so Felix result imply in particular that if we have a system which comes from one rational map F, that is, it is obtained by taking restriction of F on disjoint subdomains. If we assume that it has the same topological degree as this map F, then the quantity Tf which we called Poincare exponent, is equal to the hyperbolic dimension of the Julia set of F. So this was some excurse into three pressures. Now let's come back to
Maybe
Macmillan.
Denker and Turbinsky.
Sorry?
Denker and Turbinsky also
Mhm.
more or less the same, and how it's certain and described in our book is Michel.
Mhm. I see.
Okay, go on.
Sorry?
No, I finished.
Okay. Mhm. Yes, thank you for the remark. Now, similarly to the case of real quadratic polynomials, we define we define Macmillan's matrix for system curly F. Basically, given two domains UI and UJ of our partition, such that preimage of UJ intersect UI, we take supremum of the derivative over this intersection and raised to power minus t. But since the degree, so our map now can have critical points on elements of our partition, we need to multiply by the degree di, topological degree of our map Fi on UI. Otherwise, dimension is similar to the real quadratic case. So denote by rho of A spectral radius of square matrix A, which is the maximum of the absolute values of the eigenvalues of A. And similarly to the real quadratic case, we denote by delta the infimum of negative t, for which the spectral radius of the Macmillan matrix is equal to 1. Or infinity if this infimum does not exist. We show that for the systems F such that its post-critical set closure of the orbit of critical points does not cover all image of the domain. The number delta F is well defined and is less or equal than the exponent TF. So in fact, this condition is not needed in particular cases for instance for rational maps, as so Felix showed this quantity delta F makes sense even if this set has non-empty interior. It is sufficient to consider non-exceptional points Z instead of this condition. But in our generality, for simplicity, we consider this condition. And several remarks, practical remarks on using this theorem for computing lower bounds. So this quantity is equal to hyperbolic dimension, which is less or equal than Hausdorff dimension. To improve bounds, we can take refinements of systems. Refinement just means that we have subdivision of initial partition and restrictions on the corresponding maps. And for refinement, we have the corresponding tree pressure satisfies this inequality. And also, it is not hard to see that the spectral radiuses of the Macmillan's matrices satisfy similar inequality. When we take a refinement, it can only increase. And so the lower bound delta corresponding to refinement will always be greater or equal to the delta of f. And thus, taking refinements improves lower bound of the Hausdorff dimension. Moreover, if we take sequence of refinements, the sequence of the pressures is increasing and converges. Assume that these systems f came from the same rational function f and have the same topological degree. Assume additionally that the maximum of the diameters of all tiles converge to 0 when k goes to infinity. Under this condition, Felix Trutitsky showed recently that limit of this lower p pressures coming from Macmillan's matrices converges to the true geometric pressure of rational function f. And this implies that the lower bounds which we obtain from Macmillan matrices converge to the hyperbolic dimension. So we know in this case that sequence of approximations are actually true approximations. They converge to the hyperbolic dimension when we take smaller and smaller partitions. But the question remains how fast they converge. That's why we cannot yet obtain precise bounds, only lower bounds in the complicated cases such as the Feigenbaum maps. Now let me briefly talk about the proof. It's rather straightforward. So assume we have a system of holomorphic maps F as above. So to recall, the main conditions are that the domains are disjoint open sets, and we have transitivity property. Then if we assume that we so our collection comes from the same rational map F, we have Julia sets defined, and we can introduce the usual Poincare partial series and usual free pressure. The Macmillan's matrix M of T has the following entries. So what we want to show? We want to show that the spectral radius of M of T is always less or equal than exponent of the Poincare exponent of the pressure function P. And this would imply that delta Vf, which is the infimum of values for which spectral radius equal to 1, it will be less or equal than Tf, which is the first zero of the tree pressure. Now we notice that the spectral radius of matrix M can be obtained as limit of this quantity. We take norm of M of T raised to power K and take raise it to power 1 over K. To prove our inequality, we'll compare entries of the case power of Macmillan's matrix with terms of the case partial sum of the Poincare series. For simplicity, we will fix starting point Z. Consider preimage of Z under case iterate, denote by Zj Fj of W for this preimage. So in particular, we have Z0 equal to W, Zk equal to Z. And if our initial point is inside the domain U, or rather its image, then we can mark which regions of our Markov partition we visit. So let I0, etc., Ik be such that Zj is inside Uij for each j. Then, so the derivative of case iterate on W, a term which appears in the quantity theta k. So this is product of derivative at points Zj. But each of these points Zj, we can, or rather each of these derivatives, we can replace by the suprema of the derivatives over points from the same region Zj belongs to. This is trivial inequality.
May I make a comment?
Yes.
Here you have W and you want to replace it by, you take supreme over Y, you want to replace it by I's. And in my paper in bulletin, have in mind that I recent made various attempts so that we don't need to consider supreme, but just 2 points, and rather one antipodal to the other with respect to this W, and at least one of them we have derivative. You told me that it doesn't help that we don't need to consider supreme, but just 2 points. But there's such a variant of that I played with definition.
Yes, I think that if we want to have a rigorous lower bound, then we need to take supremum if we take pairs of points, I guess
we are close to supreme. I just want to say that if we take one just any, then the antipodal must be on the other side of this W. So I just say to have supreme, you need to make a 2 or maybe depending on degree final number of attempts.
Yep.
So,
Yes, in our case, to calculate this supremum, we just need to look over the boundary, of course, of the corresponding piece.
not the
It, of course,
boundary, that's what I
sorry?
The boundary, okay, it's enough, of course, but maybe not the whole boundary. You just need to use bounded number of attempts in your bound.
Yes, yes, and control the error terms. Of course, we cannot give precise bounds for continuum of points. We rather take a collection of points on the boundary and control error terms using various techniques. So for our purposes,
No, but I just want to say you can take any point in the boundary, and if it is bad, I mean close to critical, then the podal in the cell is already like supreme. That's good. Okay, thank you, sir.
Yes. Okay, so we have this inequality. And then when we raise to power minus t and each side of the inequality and sum up over all w, all these preimages of point z, for simplicity, we assume that we consider only one preimages in one domain. Then we obtain this inequality because these pieces, these terms are elements of the matrix. So these are product of k elements of matrix M of t, such that the next element is in the same row as the column of the previous, something like that. So when we sum up, we obtain exactly the entry of M of t raised to power k. And here on the other side, we obtain exactly the value theta k, which implies the desired inequality. When we raise this to power 1 minus 1 over k, in the limit we obtain exactly this inequality rho of M of t less or equal to exponent p of t f, which finishes the proof of the main theorem. Now, so it's surprisingly simple and it demonstrates that no one did it before, maybe because of the technical reasons. Because it's hard to make accurate numerical calculations. Now, let me just say a few words about computational considerations. So let us come back to the real quadratic polynomials. The corresponding tiles of the Markov partition. To approximate rigorously the boundary of each element of the Markov partition, we cover it by disks. Then, when we take preimage of each disk, we have two preimages. We can estimate using standard tools of complex analysis how large will be the preimage and cover it respectively by another small disk. And we obtain sequence of coverings of the Markov partition, which allow us to obtain rigorous estimates. Next, to compute, to make our estimates, it is convenient to use certain type of circular arithmetic. So assume we want to take a preimage of disk under z square plus c. For that, we consider disk MR, which we denote simply by one letter bold Z, and introduce operation on this disk. So we need to introduce two operations: difference of two disks, to make sure that the image of our operation is covered by another disk. We need to sum up the radii. And also we can define root of a disk. So again, making sure that we obtain a new disk which will be covering all preimages of points from the initial disk. So we enlarge our set to make it a disk again. And this is just a convenient way of representing boundary for computing computational purposes. And finally, remark on computing spectral radius. Given n times n matrix when with non-negative coefficients, Collatz showed the inequality for the spectral radius as follows. We can take any vector v of positive with positive entries, take its image w, and spectral radius is always greater or equal to minimum of ratios wi over vi and less or equal to maximum of the ratios wi over vi. And taking subsequent images, this bound actually gets better and better. This allows to compute accurate approximation of spectral radius even for very large matrices. Okay, that's it. So I finished quite quickly. So that's thank you for attention. Any questions?
Any questions?
Yeah, may I ask a bit maybe naive question, but maybe I'm missing something simple. Why do you consider the partition that you consider not like Igors puzzles?
Because it's easy to calculate. The task of computing the images of sets is already complicated enough if we take say 30s per image, and then we need to construct McMillan's matrix and approximate its spectral radius for various t. Just starting with disks seems simpler than using other types of partition in this case, just for simplicity of calculations.
But let me give some maybe complementary answer. Your cost puzzle, you start with fixed point and pre-images, etc. And if the mapping is renormalizable, you never go to partition into points. So you need to start again and again some original cost puzzle and continue. And here, this one, which has critical value of the boundary and critical points, is better because diameter shrink to 0. Am I right?
Yes.
No.
Well, actually, for Feigenbaum maps, for instance, yes, but so for hyperbolic maps, actually, it's not true. Because we have, so let me see if I have a picture of the hyperbolic case. I don't remember. It seems that, yes, I don't have a picture. But basically, we always have 0 on the boundary of 4 tiles. Even for hyperbolic polynomials, for simplicity of calculations, we don't care about cutting out disks from the attracting set. And so for hyperbolic case, our partition does not converge to 0 in the diameter, but we believe that it does not affect accuracy of the approximations. So there will be some tiles which are narrow and thin, but anyway, the suprema of derivatives is at the point furthest from the origin, and typically it will be on the outer boundary, and so it doesn't matter if we take small regions. For us, it's important that the outer boundary of our regions converge to the Julia set, so to say. But it's a possibility for hyperbolic Julia sets. You can also cut out orbit neighborhood of the orbit of periodic point, and then this will be true that the diameters of all tiles will be convergent to 0. So yeah, I hope the answer was not too confusing.
Thank you, Jonathan.
Thank you very much.
Okay.
Biscuits, tea, coffee. No, so sorry.
Yeah.
Carol, are you in Europe already or in?
No, I am back in Budapest.
I see.
Uh,